Swayam Prabha. Digital India. Educated India.
Welcome back. So, we were discussing Bitcoin scripting language, and we ended by saying that Bitcoin scripting language is not Turing complete. And what that means is that we cannot express arbitrary functionality with Bitcoin scripting language. Very simple things can be only expressed with such a restricted language. Now, what happened is that when the users of Bitcoin saw that the limitations of this, then the Ethereum guys came in and they said that we need a much more expressive language. So, they created a new language called Solidity, and in Ethereum they started using Solidity to write this kind of complex functions, and those are called smart contracts. So, the Bitcoin scripts are actually precursors of smart contract, and we will see in a few within a few slides that the Bitcoin script, even though it is very restricted, still can express a number of things that are very useful and interesting. But before that, let us see what the Bitcoin script execution looks like. So, let us say I have this after concatenating the SIG script and then the script pub key, I have this. So, this part is actually part of the script SIG, and this is the script pub key, and we have concatenated them. So, this is my complete script, and I want to execute this in a stack based machine. So, what happens is that the first now things that are expressed with the angular brackets are data, because this is just a prototype example. So, we do not have real data here. In the actual case, there will be a signature, there will be a public key which will be actually data, right, and therefore, and this will also be data, and rest are instructions, right. So, whenever we are seeing these angular brackets, those are data. So, as I said that when I encounter data while executing, I push them on top of a stack. So, let us look at the stack. So, when I encounter SIG, I will put that on the stack. Now, next I see that there is another piece of data. So, I have to put that on top of that. So, I will put that also on top of the stack. The stack grows. Now, I encounter an instruction opt up. So, when I see opt up, what it does is it duplicates the top of the stack. So, when it duplicates the top of the stack without removing what was on top of the stack. Some instructions remove the entity on top of the stack, but opt up basically keeps the entity on top of the stack. So, it creates another copy of this key, and we will understand very soon why it did that. Now, the next one is another instruction. This instruction is saying that hash whatever is on the top of the stack, right. So, it is going to hash this top of the stack. So, and this one replaces what was on top of the stack. So, now we have the hash of the public key on the top of the stack. Now, I encounter another data. So, I put it on top of the stack, right. So, I have now this data and this data. Then I have another instruction which says equivalence verify. So, which means that take the top two elements of the stack. This instruction semantics is that you take the two elements on the top of the stack and verify if they are equal. If they are equal, then it will return true, which means those two things will disappear from the stack, but nothing will be pushed on the stack. So, now I have done that. So, now I have only the public key and the signature, and then I encountered the next instruction which says check the signature. The signature is done with the private key. So, if this public key is the correct public key for this private key, then we will be getting a verification, otherwise the verification will fail. So, if assuming that the verification passes, then it is going to be empty stack, or it will be all true, and then I have succeeded in executing this entire script. Now, let us look at this at a little bit more closely. So, the guy who is spending the money, he does a signature and he gives his public key, because without the public key one cannot check the signature. So, he gives his public key. Now, if the users want, they can check from other places, because public key is a public information, that this is indeed his public key, right. So, he puts the public key and he signs with the private key. So, this is the input part of the transaction gives. The output part of the transaction is supposed to only give you the public key hash, right, of the person who is supposed to get the money. What it does is that I am going to check whether this public key hash matches with the public key of the recipient. So, for this what I am going to do is that I am going to duplicate the public key, and then I will make a hash and I am going to compare it, and then I am going to check verification of the equality, and if they match, then we know that this is the correct hash. And then I will check the signature. I have the public key, I have the signature, so I can check the signature. So, this is how this thing actually makes sure that the spender of the money is indeed the correct spender, has the authority to spend that money. Now, remember one thing I forgot to tell you is that you actually take this part. So, when you put together this, you take this from your current transaction and this part you take from the previous transaction. Why? Because see this is the part, see current transaction, in the input part I put this, I signed it, and this is the in the output part of the previous transaction which I am trying to use, right. So, this is not the output of the current transaction, this is the output of the previous transaction, and this is the transaction which is being used for as input, and this part is from the input. So, in the input I put my signature saying that I am referring to so and so transaction on which so and so output 0 or 1 or 2 whatever is I am going to redeem. So, what this has to do is that it has to take that corresponding outputs from the previous transaction, corresponding outputs, output pub script, script pub key, and then concatenate them together. So, it is not that the input of this and the output of the current one, input and output of the current transaction are concatenated. It is the input part of the current transaction, and this part is from the output of the transaction referred in the input. So, that is very important, otherwise you will be confused when when you try to understand this part. Okay. So, this is the how the execution happens. So, it is completely stack based, and the script, Bitcoin script instructions 8 bits long, and so there are 2 to the 8, that is 256 different possible opcodes. But right now there are 15 opcodes that are not used, they are disabled, and 75 are reserved, but those opcodes have not given any functionality yet. So, out of 256 you subtract 90, so you have 166 possible opcodes. So, some of the opcodes are just arithmetic. In our example we did not see any arithmetic, also some if then, some logic or data handling, and crypto functions like hash, computing hash, verifying signature, verifying multiple signature, things like that. So, that is what the very simple and small language. So, multisig is an important opcode. So, what it does is that it specifies n public keys and specify a number t, and if you want to verify joint signatures, you require that t of them should verify, right. So, not all n necessarily have to be signing to verify it, but at least t of them should verify. Now, if you specify t as n, then you would require all the n entities to sign the transaction for the transaction to be valid. Now, there is a bug which was there, and in the beginning, that there was an extra data value that is popped from the stack and it is ignored when the op multisig is executed. Remember, each opcode when I get the opcode, I often get the top of the stack or 2 top things on the stack or 3 top things on the stack and use it for executing the instruction. But in this case they unnecessarily pop another extra value, and therefore, when you write your script, you have to add that repeat that data value that gets unnecessarily popped, which is an annoyance, but it can be done. So, in practice most nodes whitelist known scripts. With 160 or so opcodes, you can write many scripts. Some of them actually are probably meaningless, but you can write a lot of scripts. Some of the scripts are maybe malicious, doing something that you wouldn't want to do and you do not know that it is malicious. So, most nodes what they do is that they whitelist a number of scripts, and if the script, if any script differs from their whitelisted set of scripts, then they actually do not even validate the transaction and declare the transaction to be invalid. 99.9% scripts are actually simple signature check, the one that we saw and we executed on the slides, and about 1 in 100 is multisig script, and there is another thing called pay to script hash that we will discuss shortly. That is another type of script that we see about 1 in 100, and then remainders are errors and something called proof of burn. So, we will also see what that means. So, proof of burn is an instruction. So, what is a burn? Burn means that you are burning money, right. So, if you take some Bitcoin as inputs and then you say that, but you do not specify who gets it, but the script executes fine, then that Bitcoin becomes irredeemable, which means that you cannot redeem it ever again, because once you have used it as input, you cannot use it as input to another transaction. On the other hand, in this transaction you do not create an output, so you cannot refer to that output to do the next transaction. So, that Bitcoin goes nowhere, right. So, nobody can use it. So, we say that we have burned that amount of Bitcoin. So, why would I need to do that? The reason is that the way the proof of burn happens is that there is an opcode called op return, which returns without error, right. Now, we said that if when I execute the script on this stack based machine, then if I have no errors, then we assume that the transaction is valid, right. So, in this case the input goes away, but the output is not going to anybody. So, therefore, the money is gone. But what happens is that op return is such that anything written after the op return is ignored, because op return basically returns the script from execution. So, you can put arbitrary data after the op return, and then the transaction will be valid, and then this transaction will be eventually go into a block and will become permanent in the blockchain. So, if you want to keep some data forever into the blockchain, then you use a proof of burn. You pay a very small amount of Bitcoin, maybe 0.00001 amount of Bitcoin, burn it, and then basically etch the data forever in one of the blocks, right. So, many times you will hear that people are nowadays giving like your course certificate on the Bitcoin blockchain. This is how this is done. The data about your certificate will be actually etched into a transaction using a proof of burn transaction, and then it will be in some block. And so, if somebody wants to in future wants to check if you have the certificate, they can actually go into the Bitcoin blockchain and retrieve that information. And since this is supposed to be non-temporable and supposed to be permanent, then this is a proof that you really got the certificate and you did not forge the certificate. So, that is how this is done. So, there is another issue that we saw that the script that we saw as the script pub key was pretty long, and not very long, but it was long, and it has multiple instructions and data values in the right places and so on. Now, suppose you are working with a merchant and you buy stuff from him, and then one day he says that, look, we have changed ownership and we now have multiple owners. Now, we actually need to sign, 3 of us need to sign before you are named. right. So, you have to send the money to a multi-sig address, right. Now you get confused because you are the sender and you are used to just regular writing scripts which are basically looks like what we just saw. It is a check sig type of thing. When it is multi-sig, you do not know, so you will be confused, and if you make a mistake in writing the script, then the money cannot be redeemed by the merchant. So, what the merchant can do is that he can give you a script, but the way he does it is that he writes a script and puts a hash pointer to that script. So, when you send the money, you do not have to write a long script, all you have to do is to actually send the money to that hash. So, this is a technique that was introduced later in blockchain. It was not there in the beginning, and this is called a pay to script hash type of payments, right. So, instead of paying it to a regular address, a person's address, you are sending it to a hash value which looks like a regular address. So, you from sender's point of view there is no change, but from the perspective of the other side, you actually have a much more complex script that you are hiding from the sender. So, what you do is that you put the hash of the redemption script, and then you check the redemption script, and if the hash matches. So, this part checks whether the redemption script to which you are sending is indeed the redemption script that you meant. This is all you have to write, like you did in case of a regular address. So, it could have been a regular address and you would have written the same thing, right. You would have written the op hash and you would have written the hash of the redemption script and then equal, right. And then, so then you do the pub key, then signature check and all that stuff, which was you would have done anyway. So, but what happens is that after you have done this, the actual script is replaced, and that script needs to be executed before the actual the entire script finishes with success. So, that is how this this works, and this is called the pay to script hash. So, the basic idea is that you actually have to the receiver has a complex business situation where he needs payment to be made to through a complex script, but you do not want the burden of writing a complex script. So, he makes it easier for you by writing a script and tell you the hash of the script, and then you basically use the hash of the script as if you are sending to a regular address, which also is a hash of size 160. So, that is all that there is to this pay to script hash. So, that is how it works. When you are ready to pay the purchase, these guys give you an basically a hash value as an address, you use that, and that is what the pay to script hash means. Now, what we will see is that even though the language of Bitcoin scripting is very simple, even with that we can do a lot of smart things, right. And what we do with those is called are sort of the precursor of smart contracts. So, we can use scripts to do multiple things, but we will show you a couple of things. So, the first thing we want to show you is the escrow transaction, and then we will also see how to do micro payments, and then we will show you how to do a green payment. So, these are the three examples we will show, but there are many others that you can do with this scripting language. But as we said that since this is not a Turing complete language, we cannot do a very complex thing with this, and therefore, we have to have a Turing complete language if we want to do very general things with the help of blockchain. And so, let us see what is an escrow transaction. So, let us say Alice wants to buy something online from Bob, and Alice does not want to pay until Bob ships and shows the proof of shipment, but the Bob does not want to ship until Alice pays. So, normally when we buy something from Amazon, what we do is that we pay it by credit card and then they actually ship the item, and then we can complain to the credit card company if the item is not good. And if we trust the merchant, then actually we can even complain to the merchant himself, in case like Amazon, and maybe we can get a refund or something. But in this case, what escrow transactions do is that it allows you to involve a trusted third party to keep the money on escrow, and then if both sides trust that third party, then the Bob, the merchant, would know that even though he did not get the money, it is put in escrow, and the escrow keeper is trustworthy. So, in case there is a problem, the escrow keeper will pay the money to Bob. So, what happens is that Alice writes a transaction that says that sends it to an escrow account, and it's a multi-sig instruction which says that it requires 2 out of 3, and Alice, Bob and Judy, who is the adjudicator or who is the escrow person. So, now Bob knows that you have put your money in the escrow, so he ships the item to Alice. Now, in a normal case, suppose Alice gets the item and is happy and they are both honest. So, then what the Alice says is that use this transaction of the escrow transaction as input and create a new transaction that is given to Bob, and it's signed by both Alice and Bob, right. So, that's the normal case. Now, suppose what Alice gets is broken or has some problem, or it never reaches, then there is a dispute, and then Judy has to decide who is at fault. If Judy decides that Bob is at fault, then she will sign this, and then Alice will get the money. If Alice is at fault, then Bob will get money, right. So, this is how the escrow transaction works. So, you are basically putting the money in an escrow until both sides are satisfied. It remains in escrow. If there is no dispute, then normally 2 sides sign. It is a 2 out of 3 signature. If there is a dispute, then Judy has to decide, and Judy will sign with whichever party should get the money. Now, there is another thing called green addresses. So, in green addresses, what happens is that, say, a similar problem, Alice wants to pay Bob, and Alice makes the payment transaction, but Bob cannot wait for 6 verifications. Remember, like we said, that there has to be 6 blocks built on top of the block that contains this transaction in the blockchain in order to be probabilistically more sure. So, and also Bob does not want that Alice then goes around and does a double spending. So, all this stuff, or Bob may be completely offline and he has no way to check what is happening. So, what Alice can do, he can go to third party. In this case, we call it a bank, or it could be a cryptocurrency exchange, some entity that what they do is that and they have a relation with Alice, they trust Alice, or Alice might have a lot of money in the bank or lot of cryptocurrency in the exchange or whatever. So, Alice says, could you make out a green payment to Bob, and then the bank says, okay, I will make a green payment to Bob. So, what it does is it puts a transaction that pay to Bob and Y to bank. The Y to bank part is for maybe for fees that it charges Alice or whatever, and then Alice will then make a transaction with the bank to settle this, and then it gives a guarantee of no double spend, because Bob actually does not know Alice well. So, Alice he cannot trust, and therefore, even if Alice paid X to Bob and it comes as a transaction on the network, Bob does not know that Alice will not now use the same input to another transaction and give it to her, give the money to herself. So, that would be a double spend, whereas bank is a more trusted entity. So, it probably will not do double spend because it worries about its reputation. Also, it may have some kind of a certificate that says that it has not made a double spend transaction in so many years or whatever. So, Bob trusts the bank and Bob then ships the item. Now, what happened in the double spend case is that the exchanges, when they started this green address idea, people were excited because let us say you are ordering food. So, the merchant cannot wait for 1 hour for 6 verifications to deliver your food. So, green addresses idea was very welcome. So, that the with the Bitcoin transactions also you can buy things which can be delivered fast. On the other hand, the merchant is also guaranteed to be paid eventually, even though he may not know the customer. But turns out that Mt. Gox we talked about in a very beginning. Mt. Gox was one of the exchanges that used to provide these green addresses and green payments, and there were a few other, but they all actually have run out of business. So, green addresses nowadays is not very common because it did not really work out for other reasons, mostly outside the technology reason, but so green address is a good idea, but it did not really work that well. The third thing that we want to talk about is efficient micropayments. So, what is a micropayment? Say Bob is a mobile service provider, and it charges Alice by the minute, right. So, when Alice is making a call, then one possibility is that Alice's whatever client she is running, as the minutes tick, she pays Bob payment for 1 minute, and then make another payment for second minute and another payment for third minute. But every time she does that, first of all, she will put too many transactions on the network, because this scenario could be very common if it is let us say Airtel, and Alice is an Airtel user, and therefore, this is not very efficient. Second thing is that the Alice might incur fees per transaction, right. So, she does not want to do so many transactions, so she has to pay more fees. It may be like per minute payment may be less than the payment for putting transactions into blocks. So, therefore, the idea of micropayments came into existence. So, what we do is that Alice initially pays an amount y, let us say 100, or the maximum that Alice thinks that she would need to make this phone call from her whatever input transaction that she is trying to redeem, and then it is a multisig, and it is only signed by Alice, and this is not signed by Bob. So, therefore, this is not going to be redeemed yet, and then per minute a new transaction is created which is signed by Alice. Bob does not sign them. So, now we are doing a number of double spend. So, this is your X transaction, and this is kind of like you made this payment, and then from this transaction you are redeeming this transaction, although this transaction has not completed yet, you are redeeming this transaction with 1 to Bob and 99 to Alice, and then next minute you pay 2 to Bob, 98 to Alice, and so you are doing lot of double spends. But none of them are being redeemed, or they are actually not even put into the blockchain, because all of this cannot go through, because they are referring to the same transaction and doing various different things, and they are all double spends. But at the end, when Alice says I am done, and Bob says okay, I will publish the transaction on the blockchain. So, what he does is that he signs the last one of them and then publishes it. So, what happens now is that the last amount that is due to Bob, so let us say it was 42 minutes. So, then Bob gets 42 and 58 goes back to Alice. So, all the other previous transactions are not put on the blockchain, and therefore, and even if Bob tries to put them on the blockchain, it will not work because it will be a double spend. All these transactions are referring to this transaction, that is why it is a double spend, as we explained before. So, now there is a possibility that Bob never signs this transaction. Now, what that means is that Alice will lose this 58 also. She paid 100 before, and then now she has this 58. This one was actually put into the blockchain, but it was not signed by Bob. But now Alice has a possibility of losing the 58. So, therefore, there is a thing called timed refund transaction. So, in a timed refund transaction, Alice demands that when she does this one, Alice demands that the Bob does another one in which Bob signs and says that pay 100 to Alice, and this is, remember the lock time. The lock time is what we use here, and therefore, the lock time will be set to some t, appropriate t, so that if Bob refuses to sign this one, then Alice can, Bob already signed this. So, Alice can sign this and get all 100 back. So, that is where the lock time thing that we saw before is. So, usually we put lock time 0 for immediate use of the transaction, but here we put a time t, and therefore, we Alice can get back all the money after time t. We will come back to this in the next session. So, for now we have seen 3 different use of Bitcoin scripts to do more complex transaction than just paying from one person to the other.